All right, in this video, what we're going to be looking at are something called ice tables and looking at what's called a Ka. So this is going to be the last part in our acid-base solutions notes. So the first thing that I want to talk about is this idea of strong acids. Strong acids dissociate 100% in solution. And when I mean that they dissociate, it also means that they ionize, so they form ions. And there are 7 strong acids that you need to know. So I have them written on the screen. So we have chloric acid, hydrobromic acid, hydroiodic acid, hydrochloric acid, nitric acid, perchloric acid, and sulfuric acid. All other acids are actually considered weak. So if I were to look at what these look like and what the difference is I have them right here. So SA stands for strong acid. So hydrochloric acid is a strong acid. And notice that arrow. That arrow is only pointed in one direction. And what that means is that when hydrochloric acid is in solution, 100% will dissociate and turn into ions. So when the reaction has reached what's called equilibrium, when it has kind of, in a way, stopped, we have all hydrogen ions and all chlorine ions. There is no HCl as a compound in that solution. However, if you look at the weak acid, that WA stands for weak acid, here we have acetic acid. And acetic acid is a weak acid. And notice the arrow is 2 ways. What that means is that when that reaction has come into equilibrium, not all of the acetic acid has broken into ions. Some have, and we do get some of that hydrogen ion and that acetate ion, but still in solution is that weak acid, acetic acid. So we have all 3 of those species or all 3 of those substances in solution. Now, strong bases are the same way. They will dissociate 100% in solution. And in order to identify strong bases, we use our solubility rules. And our solubility rules says, in general, hydroxides are insoluble in water, except when they're bonded to a calcium ion, a barium ion, a strontium ion, alkali ions, or ammonia. So here we have the same thing. We have a strong base, some lithium hydroxide, and it will 100% turn into lithium ions and hydroxides. A weak acid, like ammonia, when it reacts with water, will create ammonium and hydroxide. But again, notice that 2-way arrow. That tells me that all 4 of those species will still be in solution. They won't all turn into ions. Now, ice charts are very helpful. Ice charts are going to be a tool that we use to solve some mathematical problems. So they allow us to organize our variables and understand how things might be changing during a reaction. And I stands for I, which is initial, so we want to know what are the initial amounts or conditions before the reaction has started. C is change, how the variables change during the reaction, so what's happening. And E, which is end, so the amounts or conditions when the reaction ends. So these ice charts are actually really powerful tools that allow us to analyze a reaction and what happens. So what we're going to do is we're going to solve this first problem. So the problem says we want to find the concentration. Those hard brackets, those square brackets mean concentration. So we want to find the concentration of our hydrogen ion, our hydroxide ion, our hydrochloric acid, our chloride ion. We also want to find our pH and pOH for a 0.100 molar solution of hydrochloric acid. So we're going to go ahead and switch screens, and we're going to solve this problem using our ice tables. So here's our example. What I've done is I've gone ahead and I've rewritten my ice table. So the first thing that you want to do when you approach this problem is you need to ask yourself, is hydrochloric acid, HCl, a strong or weak acid? So will it dissociate 100% or will it not? And the answer is that it will. And that actually makes our problem a lot easier, knowing that it will dissociate 100%. So what I'm going to do is, at the top of this table, I'm going to go ahead and I'm going to write out this dissociation reaction. So I have HCl And I'm going to show a one-way arrow, and it's going to break up into some hydrogen ion and some chlorine ion. And then what I want to do is I want to fill out my initials. So remember, my initial is before it breaks up into its ions. So what I'm told is that I have a 0.100 molar solution. So what that means is that initially I have 0.100 molar of my HCl, but this is initially, and so initially we assume that nothing has broken apart. So I have nothing in those two categories. Now my change, well, what's going to happen is that my 0.1 molar of hydrochloric acid is going to turn into ions. And it's going to turn into ions and it's going to dissociate 100%. So I'm going to go ahead, I'm going to say minus 0.100 molar. And note that these are all 1-to-1. So this is going to create a 0.1 molar hydrogen ion, 0.1 molar chlorine ion. And so my ending is going to be no hydrochloric acid, but I'm going to have plus point, or actually I don't even need to put the plus. So go ahead and erase that. I'm just going to go ahead and put 0.100 molar and 0.100 molar. So now my question becomes a couple different things. So it asks, what is my proton ion concentration? So my concentration, my hard brackets represent concentration. So that is going to be 0.100 molar. It also asks, just based off of this, I'm going to skip one, my chlorine ion is 0.100 molar. My concentration of my HCl, well, is 0. So now I need to find my concentration of my hydroxide, so my OH concentration. And there is a reaction that we can use. We know that Kw equals the concentration of the proton ion plus the concentration of the hydroxide. So if I rearrange this and I solve for my hydroxide, what I see and what I'm going to get when I plug everything in is I'm going to get that my concentration of my hydroxide is going to be equal to Kw. Whoops, let's put that as a subscript. Kw divided by the concentration of my proton. Now I can plug in the variables that I know. I know what Kw is because that is just a constant, so I can go ahead and plug that in. And I do know what my proton concentration is because, well, I solved for that. So what this is going to be is it's going to be OH is equal to 1.0 times 10 to the negative 14th divided by 0.100 molar. And what this means is that the concentration of my hydroxide is going to be 1.00 times 10 to the negative 13th molar. So I have that. So I have the concentration of my proton, hydroxide, HCl, chloride ion. Now I need to find my pH and my pOH, and I can use those with the concentrations that I have. So if I want to take the concentration of my pH, it's going to be the negative log of the concentration of my proton, which is going to equal the negative log of 0.100 molar. And for that, that is going to be 1. So my pH equals 1.00. Now you could do the same equation for your pOH, except you can use your hydroxide. But what I'm going to do is I'm going to go ahead and I'm going to use the equation that says 14 is equal to my pH plus my pOH. So what that means is if 14 is equal to 1.00 plus my pOH, that means that my pOH equals 13.00. So those are my values that I have. So now I have my pH and my pOH for that solution. So that is how you use your ICE table. Now for this example, it was pretty straightforward and not too complicated, but what we will see is that in other examples, this ICE table becomes really important because there's more variables and there's more things occurring. So we'll go ahead and go back and we'll look at an example where this ICE table becomes a lot more powerful and provides us with a lot more information. Now Ka. So what we're going to do is we're going to look at a very simple example of a weak acid. So we have HA. Remember, our acids almost always begin with an H, and it is bonded to a negatively charged ion. So acid goes back and forth into equilibrium with its ions. And our Ka is a ratio, and it shows what is the concentration of my ions, that H and the A, over the concentration of my original acid. And that Ka is really important. It's a ratio of dissociated ions into weak acids in solution. So that Ka will change depending on how many ions are in solution. The larger the Ka, that means that we have more ions in solution. So that top part of that equation has higher values in the bottom. And if we have more ions in solution, that means that it is a stronger acid. The smaller the Ka, the fewer the ions are in solution, therefore the weaker the acid. So this Ka value is really important. It tells us something about the strength of the acid. Is it a strong acid? Is it a weak acid? And exactly how weak is it? How many ions will we have in solution? Another way of looking at this is talking about what's called our percent dissociation. So what is the percentage that these ions actually dissociate? And we can actually solve this by taking the amount dissociated, dividing it by the initial amount, and multiplying it by 100%. Now we're going to go ahead and we're going to look at another example where we're going to be using these Ka values. We're still going to be using an ICE table. So in this problem, it says we want to find the concentration of the proton, the concentration of the acetate ion, the concentration of acetic acid, the pH, and the percent dissociation for a 0.100 molar solution of acetic acid. And we are given that the Ka is 1.8 times 10 to the negative fifth. So let's go ahead and switch screens and solve this problem. All right, so here's our example that we had on the slides. I'm going to go ahead and redraw my ICE table. And we're going to do pretty much the same thing that we did last time, but there's a few different steps that we need to take. So let's go ahead and write out our reaction. Let me go ahead and finish this. ICE. Now, our reaction is, in this example, a weak acid, which means that it doesn't dissociate 100%. So when I write out my reaction, this is what it's going to look like. HC2, H3O2, and it's going to be back and forth H plus C2, H3O2. So there's my reaction. And let's go ahead and label in our initial amounts. So our initial amount says that we have 0.1 molar solution. So 0.100 molar solution. And just as before, when this reaction is, we'll say like at time 0, so when it hasn't even started, we have 0 amount of our ions. Whoops, let me go ahead and put a negative sign right there. Now, this is where it becomes a little bit different. We don't know what our change in concentration is, and we don't know what that is because we don't know how much is going to break apart because this is a weak acid. So when we talk about this, what we're going to do is we're just going to solve for X. So when it's a weak acid and we don't know how much, I'm going to say that some amount is going to subtract, and that same amount we're going to create with both of these. So I have minus X, I have plus X, and I have plus X. So some amount of my acetic acid is breaking apart, and we're going to create an equal amount of hydrogen ions and an equal amount of acetate ions. So when I write out my ending, I'm going to keep my X's in there. I'm going to take off the M just so that I can write this all in here. And it's going to look like this. Whoops, not M, X. Now, you might be looking at this and thinking, wow, we have one number and a bunch of X's. How are we supposed to solve this problem? And this is when our Ka becomes important. So our Ka, if we were to write our Ka for this problem, what it says is that the concentration of our hydrogen ion times the concentration of our acetate ion divided by the concentration of acetic acid. Whoops. C2H3O2. And that's going to equal our Ka. Now we can start plugging things into this equation. We are given our Ka. So if I were to rewrite this with my Ka, I would have 1.8 times 10 to the negative fifth. And that's going to equal my concentration of my hydrogen ion, which is just X, times the concentration of my acetate ion, which is X, divided by the concentration of my acetic acid. Now, we're going to make our lives really easy with these problems, and we're not going to go into problems where this could be a little bit more challenging. We're going to make our lives easy, and we're going to assume that this X, just this one right here, is negligible. And what I mean by negligible is that the amount that the ion or that the acid actually ionizes is very small compared to the 0.1 initial molar. So we're going to assume that just this X, assume the amount the acid ionizes is very small. And that's actually going to be really helpful because if we actually kept that X, we would have to end up doing a quadratic formula. But by taking that X out, and we'll see that it pretty much is negligible, that it's just such a small amount that we don't need to worry about it. But we would have to do a quadratic formula. So we're going to take that X out, and we're going to simplify this equation. So I'm going to go ahead and I'm going to move this right over here. So what I have is I'm going to have 1.8 times 10 to the negative fifth. And that's going to be times my 0.100 equals X squared. And what I'm going to end up getting is that my X equals 1.3 times 10 to the negative 3. So now that I have my X, I now know what some concentrations are. So what I could do, I'm going to go ahead and scroll this up just a little bit. So I'm going to start labeling off what my concentrations are. So now I know that the concentration of my hydrogen ion, which is also equal to the concentration of my acetate ion, is equal to 1.3 times 10 to the negative 3 molar. So that's that. I can also say that the concentration of my acetate, or excuse me, my acetic acid is 0.100 molar minus 1.3 times 10 to the negative third molar. And what we see, this is 0.099 molar. So the amount that it decreased is pretty much negligible, and we don't have to worry about that. We do want to figure out our pH, and we can figure out our pH because we know what the concentration of our hydrogen ion is. So remember, pH is equal to the negative log of the concentration of our proton or our hydrogen ion. So it's going to be negative log of 1.3 times 10 to the negative third molar. Now, if you notice that this has 3 significant figures, I'm going to show that my pH has 3 significant figures. And one of the important things to know is that the whole number of the pH does not count towards a significant figure. So when I say that this has 2 significant figures, what I mean is that after my decimal, I'm going to have 2 digits. So this is going to be 2.89. So when we look at pH, this first number, that 2, actually doesn't count towards significant numbers. Kind of a weird thing with pH, but we just assume that that's not significant, and so that's why we have 2 digits after that. The last thing that we need to figure out is our percent dissociation. So we want to figure out how much did this break up? What is the percentage of this that broke up into ions? So what we're going to do is that we're going to take the amount dissociated, which is 1.3, times 10 to the negative 3, and we're going to divide that by the amount that we originally had, which is 0.1 molar, and we're going to multiply that by 100%. And what we see is that this is 1.3%, so not much at all. So what that means is that when we have this reaction right up here, the amount that this actually breaks up for every, let's say, 100 molecules of acetic acid, approximately 1.3 of those actually break up into ions, so not that much, which is also why if you look at this pH isn't really that strong. I mean, it's medium strong, but it's not very acidic. It's, if we were going to have like a lower pH, something like on the scale of like a 1 or a 0.89, yeah, that would be a lot stronger. But this actually isn't terribly strong, and that's because it didn't break up into that many ions. So here's this problem. A little bit different than the first problem that we looked at, because the first problem we knew that it was going to break up into complete ions. Now when you have a weak acid, you have to have your Ka value, and you don't know how much is going to break up, so that's why we have our x's up here. So you need to solve for your Ka, solve for x, and then start plugging things in, and that's how you can identify the pH of different solutions. And also your different solutions, whether it's a strong or weak acid.